Hello everyone! Over the last couple of months, other than watching Instagram Reels, I've been working on a language model with a real experimental architecture. It's still not quite done yet, but it already has some key advantages over the vanilla GPT style models. All of that thanks to a key change I made to both dramatically lower the required memory from more than 700 megabytes down to just 45, and to have some cool features like an infinite vocabulary size. In this video, I'll explain all of its upsides, downsides, and more. So, welcome to my biggest project yet. But before that, let's take a step back, as I first need to explain how neural networks even input text, because it's not like you can just shove in a string. They can only accept lists of numbers called vectors. So we somehow need a way to turn this into that, while still preserving its meaning. As it turns out, this is exactly the problem that some smart people or Google faced in 2013. They were a part of a broader project to improve Google's arsenal of natural language processing tools, including their main search engine, whose job is to literally calculate the distances, similarities, and meanings of the words you type in. To do that, Google's AI team invented word2vec, which is the algorithm I ended up using for my model. As the name implies, it turns each word into a list of numbers, aka those vectors. The special sauce is that words close in meaning have vectors close in position. So if we think of those word corresponding vectors as coordinates for a dot in some very high dimensional space, we can see that the distance between the dot for apple and the dot for green is pretty small, since those words are associated, and so is the distance between banana and yellow. But the distance between apple and yellow is far bigger. This sounds kinda obvious, but at the time word2vec was pretty much the first algorithm that could put meanings of sentences into numbers. And today, pretty much all big language models use offshoots of this original word2vec algorithm. This word2vec model will be useful to us later, so let's train one. For the dataset, I'll use one called UltraChat. It's basically a really big text file with who knows what in it. I ended up using just a little less than 3 billion words, and the size of the vector to represent each word that I chose, also known as the embedding dimension, is 784, for no particular reason. Imagine the animations from before, but instead of using 3D or 2D depending on the budget, it's in 784D. This might seem like a lot, but in reality most quote-unquote serious language models use embedding DIMs as high as 4096. Here's the full list of hyperparameters if anyone wants to recreate it. This will take a few good hours to train, so let's check back on the results later. Meanwhile, if you got this video recommended to you, then you probably already know how GPT-like models are trained to write text. A chunk is pulled from the dataset, the last word or token is cut off, and the network is asked to predict the word that was removed. It does that by having a big layer at the end, with every neuron having its corresponding word. The predicted word is just the one whose neuron returned the highest value. As you can imagine, the final layer is very massive. And this is exactly where my key improvement lies. Instead of my output shape being the vocabulary size, which is usually between 20,000 and 40,000, I'll make my network output 784. If you recall, this was the embedding DIM that I'm using to train the word2vec model. Basically, I try to get my network to just predict the next word's meaning vector and then decode it using this function. When predicting the next word in a sequence, you can think of the normal way as just having a very long dropdown from which it can select any token. And my idea is having an area set up with those word dots scattered around. And to select a token, the network just moves the quote-unquote crosshair to the correct area, and the nearest word vector is selected from the embeddings model. Since we're now completely independent from the number of words in the vocabulary, we can have it as big as we'd like, with no need to bother with fancy tokenizers. So I just used split on space and it works fine. For that reason, let's call the new architecture REAN. It has nothing to do with lean, but instead stands for Recurrent Embedding Approximation Network. After a lot of experimenting, this is the architecture that I ended up using. On the left is the code, and on the right is some animation. When a sentence enters the language model, it's a tensor of shape, number of words, or context length, I chose 128, times 784, because each word is encoded as its own meaning vector. The first stop in the network is the positional encoder. Its job is to give the sequence a sort of repeating pattern. It does that by multiplying every word vector by a sine or cosine wave. So this one would get multiplied by 0.7, then this one by 0.3, then by 0.5, etc, etc. This pattern lets the neural net have a better feel for where each word is located in the sentence. Here it is in more detail. After the positional encoder, we have the actual body of the network, the transformer blocks. This is what's actually doing the thinking and remembering facts and other stuff. Let's zoom into a single block. The first subcomponent is the attention mechanism. This is probably the single most important part of every language model. On the surface, when the input text of shape, context length by vector size enters the attention mechanism, it helps with cases like the fire is hot and this is fire. The word fire has a completely different meaning, but its meaning vector from the embeddings model is the same. So on paper, the attention mechanism is supposed to make the second fire closer to good than hot. But the real value in it is that it lets all the tokens communicate with each other. Without it, the network would just process each word on its own without caring about what's behind or in front of it. And just like the positional encoder, this also doesn't reshape the tensor, just scales its values. So the exit shape is also context length by vector size. Let's for a second check back on our word-to-vec model, save a checkpoint of its weights and see what it had already learned. This function returns a list of the top n words closest to the input word by their vectors. Let's see if it knows colors. Plugging in blue returns other color names and related words like hues and shades. Also, let's see if it has a concept of good and bad. The word bad is clearly close to evil, but also to more surrounding words, like bad deeds, bad karma, bad fortune, etc. Good, however, returns stuff like reassuring, great, and comforting. Alright, let's let it continue training and go back to the REAN architecture. The thing around the attention mechanism is called a layer norm. After we pass X through the attention mechanism, we add it to the original version from before. You can think of it as either just a really small residual connection skipping just one layer, or as the text just trying to go through the network while everyone keeps adding their opinion onto it. The layer norm keeps all the numbers in the tensor in a small range, by subtracting the mean and dividing by the standard deviation. If we just keep adding more and more stuff on top of the original input, it will balloon in size, so we're trying to keep it at bay here. After passing through the attention mechanism and the residual connection, we hit the fully connected or linear layer. It takes in and outputs tensors of shape vector size. At first, this might seem odd, since we're trying to pass an entire sentence, again context length by vector size, through a layer with the size of a single word, which is just vector size. But what's actually happening here is that each token passes through the layer one at a time. On hardware, it looks more like the layer clones itself for each token and then all the tokens pass simultaneously, but this is irrelevant. After this step, the tensor's shape also remains the same, just the values change. As you can see, over the linear layer, I'm using some sort of activation function. No time to explain, but it's based on tanh and has two trainable parameters. Then we have the same residual connection from before. This is pretty much it for a single transformer block. And since its input shape and output shape are exactly the same, we can stack them. Zooming back out, I used 4 transformer blocks in the whole network. It takes in a tensor sentence and returns the same thing. And there's nothing more to it. By now, the word-to-vec model from earlier is finally ready. Let's try some more advanced tests about pop culture and stuff. For the input 2077, the same function immediately associates cyberpunk and other video game names, which gave me an idea to test different numbers. Because when you think about it, even though there is nothing inherently special about 2021 or 2020, people associate these with other current year numbers. But when someone says 3090 or 2080, you immediately know they're talking about NVIDIA graphics cards. I also decided to test 1984, and surprisingly, it's pretty close to Orwell, which is the author of this book. That's pretty decent knowledge for an embedding dimension of only 784 and a vocabulary size of 34,000. I decided to make it so big because the REAN architecture doesn't actually depend on the vocabulary size, so the weight doesn't increase. Alright, we finally have all the parts we need to assemble the final thing. Let's do a quick recap. A sequence enters. It gets encoded into a tensor of shape 128 words by 784 vector size. It gets processed by the REAN neural network and comes out another tensor of shape 128 also by 784. But wait, 128 by 784 represents a whole sentence, not a single word. Well, I kinda lied in the beginning. GPT-like models don't predict a single word, but in fact they predict a whole sequence, shifted one word into the future. When training, they do something more like this. Pull a chunk from the dataset with context length plus 1 tokens, which is 129 for me. The input of the network is the first part, and the expected output is the second part. Basically, it gives you more bang for your buck when you're training. But still, when we're generating text, to get the next word to be added to the sequence, we can just take the last vector returned, which is coincidentally the future word that hasn't been written yet. The GPU that I'll be using for training is the NVIDIA A10G. It has 24 GB of VRAM, 7680 CUDA cores, capable of 240 teraflops. It's pretty similar to the RTX 3080, except that it only has 10 GB of VRAM and is capable of just 30 teraflops for tensor multiplication. Also figured I'd mention it here, you can use my life hack of just draining the credit card linked to your AWS account just before the end of the month to get infinite free servers for life. So anyways, after a couple days of training on approximately 16.5 billion tokens, which came out to less than 1 epoch, so I was a bit over ambitious, and using MSE loss because it's regression, not classification like the other models, these are the results. But before that, this video is brought to you by Private Internet Access VPN. By redirecting your traffic through a worldwide network of proxy servers, PIA lets you teleport from anywhere to anywhere at any time with the click of a button. So no one can pull your IP anymore, and you can access any region-locked content. By also encrypting your data on their side, Private Internet Access ensures that you can use any unsecured public network like coffee shop Wi-Fi or God forbid the school internet without any risk. So please, if you want to support my gambling addiction and get a sweet 83% off on one of the world's top VPN, let the link in the description be the last one you click unsecured. Now back to the video. First of all, the train and validation loss graphs look pretty good. Of course I should have gone further with the training, but this already took long enough. Now let's try actually talking with it. First, I tried asking for a garlic and potatoes recipe with the following prompt. Human, how do I cook potatoes and garlic? Network. First of all, I figured I'd explain why I need these human network tokens, because the dataset is mostly made up of a person talking with what I assume is ChatGPT. And those tags are just there to differentiate who is talking when. And for that prompt, the model completed: the sauce stuffed is a popular destination for its unique flavors and flavors. The chili mustard is a popular destination. Well, you get the point. Let's see if it can give me recommendations for graphics cards. I also decided to trick it a bit and try to get it to complete my sentence as human without immediately transitioning to network. And the completion is absolutely terrible. It just keeps repeating graphics over and over again. But the weird thing is, when I tried testing it earlier in the training around 20,000 batches, the previous example was from 160,000 batches, the specific example had worked way better. And graphics that are worth exploring? Network. Yes, here are some popular graphics and graphics, apparently. 1. The graphics. 2. Approximately the same thing. 3 and 4. I like the way that I tried making a list with those 1, 2, 3 and 4 sentences. If I leave out the prompt completely empty, it starts talking about movie related stuff. Human, how does the connections affect the overall mood? Network, as an AI language model, I do not have personal experiences, but I can provide some information based on research. The cinematography of the movie, and you get it, I'm not gonna read the whole thing. It actually says that as an AI language model sentence quite a bit. So at least it learned something from ChatGPT. As I said in the intro, the neural net itself came out to 45 megabytes. Just for context, ChatGPT is around 500 gigabytes if I recall correctly. But the embeddings word-to-vec model isn't weightless either. It actually came out to 2.22 gigabytes. If you consider it as part of the neural net's weight, then its performance is absolutely terrible for its weight class. But since it doesn't need to be on the GPU when running, and is just used to translate the text back and forth, this thing can probably still run on a calculator. Obviously, this is pretty terrible performance, on par with most random word generators online. As usual, all of the code is fully open source on GitHub, which you can find in the description, so you're welcome to help me work on it. If you want to run the training yourself, you might need to adjust the batch size to fit your GPU. Thanks for watching.